Welcome back to Click Future, where your future is a click away. This is the fourth episode in our Quantum Horizon series, where we explore the fascinating intersections of AI, quantum computing, and space achievements. Imagine two particles separated by vast distances, even opposite ends of the universe, yet somehow remaining instantaneously connected. Change one and the other changes two. Faster than light could travel between them. This phenomenon troubled Einstein so deeply that he called it spooky action at a distance and spent years trying to disprove it. But far from being disproven, quantum entanglement has been confirmed by countless experiments and is now being harnessed for revolutionary technologies. Today, we're diving into the strange world of quantum entanglement, the phenomenon that powers quantum computing, enables unhackable communications, and might even help us understand the fundamental nature of reality itself. Einstein famously said, "God does not play dice with the universe," but as we'll see today, not only does the universe seem to play dice, but those dice are mysteriously connected across space and time. To understand why quantum entanglement is so revolutionary, we need to go back to the early days of quantum mechanics in the 1920s and 30s. Quantum mechanics was revealing a world where particles could behave like waves, exist in multiple states simultaneously, and seemed governed by probability rather than deterministic laws. This probabilistic nature of quantum mechanics deeply troubled Einstein. He famously debated with Niels Bohr, arguing that quantum mechanics must be incomplete, that there must be hidden variables determining outcomes that quantum theory wasn't capturing. In 1935, Einstein and his colleagues Boris Podolsky and Nathan Rosen published a thought experiment now known as the EPR paradox. They described a scenario where two particles interact and then separate. According to quantum mechanics, measuring a property of one particle would instantaneously determine the corresponding property of the other, no matter how far apart they were. This seemed to violate a core principle of Einstein's theory of relativity, that nothing, not even information, can travel faster than light. Einstein believed this paradox revealed a fundamental flaw in quantum theory. The paper stated, no reasonable definition of reality could be expected to permit this. Einstein believed the universe must be local and real, that distant objects cannot influence each other instantaneously, and that objects have definite properties whether we measure them or not. Erwin Schrödinger, who coined the term entanglement in response to the EPR paper, illustrated the strangeness with his famous cat thought experiment, showing how quantum superposition could theoretically extend to macroscopic objects. For decades, the EPR paradox remained a philosophical debate. Then, in 1964, physicist John Bell found a way to test it experimentally. Bell's theorem showed that if Einstein was right about hidden variables, certain statistical correlations between entangled particles would have to stay below a specific limit. But if quantum mechanics was correct, these correlations would exceed Bell's limit. This gave physicists a concrete way to determine which view of reality was correct. In the early 1980s, French physicist Alain Aspect conducted groundbreaking experiments testing Bell's inequalities. His results? The correlations exceeded Bell's limit, supporting quantum mechanics and contradicting Einstein's view of local realism. Since then, increasingly sophisticated experiments have confirmed quantum entanglement with greater precision. In 2015, researchers closed the final major loopholes in Bell test experiments. In 2017, Chinese scientists demonstrated entanglement between particles separated by 1,200 kilometers using a satellite. What we've shown is that Einstein's view cannot be correct. The world is fundamentally non-local. Objects can influence each other instantaneously regardless of distance. This doesn't mean information travels faster than light. That's still impossible. Rather, entangled particles seem to be part of a single quantum system, regardless of the space between them. The universe appears fundamentally non-local in a way that defies our everyday intuition. So how do physicists actually create and work with entangled particles? The most common approach uses photons, particles of light. In a process called spontaneous parametric downconversion, a laser beam passes through a special crystal, occasionally splitting a photon into two lower energy photons. These daughter photons are entangled. Their polarization states are correlated even as they travel in different directions. When we measure the polarization of one photon, we instantly know the polarization of its entangled partner. It's not that the measurement changes the distant photon. Rather, the measurement reveals information about the entire entangled system. Particles can be entangled in various properties, not just polarization, but also position, momentum, spin, and other quantum properties. And entanglement isn't limited to pairs. 3, 4, or more particles can be entangled in increasingly complex ways. One fascinating application is quantum teleportation, not of matter as in science fiction, but of quantum states. Using entanglement and classical communication, scientists can transfer the exact quantum state of one particle to another distant particle. Entanglement is not just some curious quantum effect, it's a resource that we can harness for revolutionary technologies. It's like we've discovered a new kind of connection in the universe that classical physics never revealed. Perhaps the most transformative application of entanglement is in quantum computing, which we explored in our first episode. While classical computers use bits that are either 0 or 1, quantum computers use qubits that can exist in superpositions of both states simultaneously. But the real power comes when qubits are entangled with each other. With each additional entangled qubit, the quantum system's complexity doubles. A system with just 300 entangled qubits could represent more states than there are atoms in the observable universe. This exponential scaling allows quantum computers to explore vast solution spaces simultaneously, potentially solving certain problems exponentially faster than classical computers. For instance, Shor's algorithm could factor large numbers exponentially faster than the best-known classical algorithms, potentially breaking much of the encryption that secures the internet today. Quantum computers can also efficiently simulate other quantum systems, like complex molecules for drug discovery or new materials, because they use the same quantum properties that govern those systems. Entanglement is the secret sauce that gives quantum computers their power. Without it, quantum computers would offer no advantage over classical computers. Beyond computing, entanglement enables revolutionary approaches to secure communications through quantum key distribution, QKD. In QKD, entangled particles are used to establish encryption keys between distant parties. The fundamental properties of quantum mechanics ensure that any eavesdropping attempt would disturb the entanglement and be detected immediately. China's MESIA satellite, launched in 2016, has demonstrated intercontinental quantum-secured video calls between Beijing and Vienna. Several countries are racing to build quantum communication networks, with China already operating a 2,000-kilometer quantum-secured network between Beijing and Shanghai. Looking further ahead, researchers envision a full quantum internet, a network where quantum information can be transmitted between quantum processors, enabling distributed quantum computing and secure quantum communications on a global scale. The European Union, United States, China, and other nations are investing billions in quantum internet infrastructure. Early quantum networks are already operational in Chicago, the Netherlands, and China, with more ambitious projects underway. The quantum internet will be to the classical internet what the classical internet was to the telephone network, a revolutionary leap in what's possible with information technology. The security implications are profound. Quantum-secured communications would be theoretically unhackable, protected by the fundamental laws of physics rather than just mathematical complexity. Quantum entanglement has journeyed from Einstein's spooky action, a phenomenon he thought revealed flaws in quantum theory, to a confirmed reality that's now driving technological revolutions in computing, communications, and sensing. In just the past decade, entanglement has moved from physics laboratories to real-world applications. Quantum computers leveraging entanglement are solving increasingly complex problems. Quantum networks are beginning to connect cities and countries with unhackable communications. As we continue to harness this strange quantum connection, we're not just developing new technologies, we're also gaining deeper insights into the fundamental nature of reality. The universe appears to be stranger, more connected, and more fascinating than Einstein could have imagined. If you found this exploration of quantum entanglement fascinating, please hit that subscribe button to join us on this journey through the technological frontiers shaping our future. And leave a comment below. Which application of quantum entanglement do you find most exciting or concerning? In our next episode, we'll tackle one of the most profound questions at the intersection of technology and philosophy. Can AI or quantum computers become conscious? Until then, this has been Click Future, where your future is a click away.